Wait, have you heard about that WMD player that's going to sit out next to you? Yeah, they're like passages and then they're gonna be like, well, this might actually be the most profitable season ever. They can't.
Yeah, I did get your email. I didn't get a chance to respond to it. Goal is to respond to it.
You see
Out of that,
I don't
to every extent I can. I actually had it up. That was the very, that was what was on my screen, right, when I. So I apologize.
Yeah, the Nolan Gardner. That's really great.
Yeah, but he airballed it.
All right, let's get started.
All right, that's great.
We have our homework due tonight. I know it's been an absolute slog of a homework. I apologize to those I haven't been able to get to because I have had people in my office the entire time for office hours and then some. So I've been working through that to the best of my ability. I will get to emails as soon as I can after class. If I can't do it within that office hour afterwards, there should be some time during my game dev class to be able to get to that because we're not doing terribly substantive things for me today. It's substantive for the students, but not substantive for me. So I can try to get to them then. If I'm not, if there's been an email that's been unresponded to for a period of time, I may be able to give you something like a day of an extension to make up for the fact that you need some time to work based on that feedback. But the other thing to note is that if I give you 2 weeks for an assignment, it's probably because it takes close to 2 weeks to do and not 1 week, as was the case for this assignment. So moving forward, start early, and that will certainly help to avoid the last minute crunch of half these questions don't make sense, or I thought I knew how to tackle this and then I tried it and it turns out I don't. That's all normal. That's all expected within the scope of difficult material, but that's why there are lots of opportunities to have that discussion with me, to get unstuck on things, getting stuck as quickly as possible, and then coming seeing me so that we can get you unstuck. That's what I'm here for. All right, last time we finished up some talk on the closure properties of context-free languages, and then this big limitation that we ended the day with. It's the very last slide here. It's just an algorithm for determining whether two context-free grammars generate the same language. It's pretty easy to prove that they don't. You just find a counterexample, but how do you just show that they generate the same language? That is unsolved as far as we know. So we're going to dive into today the last language class that we're going to study in detail. There are some language classes above this, and we will talk about them theoretically. The reason we have to talk about them theoretically is because they represent languages that we can't write programs for. A Turing machine is a state machine that is capable of doing everything that a modern computer can do. In fact, it's capable of more than that because it has infinite memory. If our computers had infinite memory, then they would be as powerful as this idea of a Turing machine. But we can now theoretically write algorithms that this theoretical machine would be able to compute in the same way that a physical computer is able to run instructions. So let's take a look at how we would design such a system that allowed for a one-to-one mapping of everything that we can write a program for. It becomes very useful theoretically to determine, can I write a program to solve that? That breaks down into, can I design a Turing machine that solves that problem? There's no reason to start trying to write an algorithm for something that can't be solved. One example of that is if I asked you for homework, give me an algorithm that could tell whether two context-free grammars or represent the same language. You could not do that. Or if you did, you'd be a millionaire. So we've seen two large classes of languages now, really kind of three. We've seen regular and we've seen context-free. We also saw deterministic context-free, which was a subset of context-free, but larger than regular. But we're going to see a big third class now. When we were looking at the state machine versions of these languages, we found that the only difference was that we included a stack along with the context-free languages with our NPDAs. And the fact that we just had that stack with us unlocked a bunch more languages that we could represent. The question we might want to ask, are there more powerful language classes that could be represented if we could allow for different kinds of storage? And the answer is yes, because obviously we write programs on a machine, so we at least need some kind of state machine that is equivalent to what we could produce. Of course, you could also think of trying to allow 2 stacks. What are the languages that we could accept if we allowed an NPDA but with 2 stacks instead of 1, or 3 stacks, or a queue? Or does anyone else have any other ideas for what structures? We could take a hash map with us. Why not? Any structure we could just take with us. And it turns out that no matter what we do with the concept of an NPDA, no matter what we allow for, it doesn't actually change meaningfully the class of languages that is accepted. Yes, there are some that get accepted that couldn't have been accepted before, but it's not a meaningful change. It doesn't allow for something like, now we can parse with a compiler, whereas before we couldn't without this context-free class of languages. There's no application to taking along a more or different or complicated or different structure with us. We actually need to define a new class of state machine to be able to define a new class of language that has meaning and relevance to what we do in computer science. So the idea is, what is the most powerful possible automata? How could we be able to accept or reject any language for which we could write an algorithm? For any language that could be in a finite amount of time, terminate with an accept or a reject. Any ideas for what would have to change? We allowed for a stack with infinite memory. What storage would be needed and what rules would be needed in order to map to whatever you could write a program for?
You have to be able to make states on the fly.
There will still be a control unit that has associated states, but that is a really intriguing idea of, can we make states on the fly? Is that something that you can do in a program? Imagine the execution of a Java program or any language you want to attach yourself to. In the middle of the execution from that, can you change the code? You can have a go-to statement that says, even though the next statement isn't here, just directly go wherever you want. But even that doesn't change the underlying code. Can you write code that changes code?
Yes, that's what viruses are for.
But it changes code in a very prescribed way. That's still, you can't have it change it in an arbitrary way. It still changes something that's underlying something, some other code, not its own code.
It's deterministic and you can't have that at any point in real time.
Right.
But
Yeah,
can't change
so
it.
we do still need to, that's a great idea. I love that idea actually, because if we could do that, that'd be amazing. So we are still going to need to identify some number of states and transitions, but now instead of storing things as a stack or any other kind of structure, we're just going to have an infinite two-dimensional tape. It's an array that's infinite in both directions. So let's take a look at the standard Turing machine. It's amazing to me that despite the complexity of everything that we could program, there exists a theoretical representation of that calculation that is this simple. It still blows my mind. And the fact that I will not say this, I can't say this enough, that Alan Turing was an absolute genius. And what happened to the man was an absolute travesty. I think that we could be a decade or two technologically more advanced than we are if he hadn't been persecuted to the point where he had to commit suicide. Absolute genius.
Wait, what happened to him?
He was persecuted for being gay.
Yes.
Oh, no.
Yes,
Yes.
in a nutshell, because it was World War II era and that was not accepted at the time. It was still illegal to be homosexual.
So truly monumental computer scientist who has done so much for even modern computer science that he never got the recognition while he was alive for all of the work that he did. So we're used to using a single dimensional array that has a beginning. But you can imagine now if that array could extend infinitely in both directions. This means that we have access to infinite storage, just like the infinite stack did, but the infinite stack was in one direction and you could only access the top cell. Now with a two-dimensional tape, you can access anything, anywhere, at any time, as long as you know how to get there, where it is. So information on the tape is both readable and writable. Kind of like the stack was, we could read from the stack, but we could also replace the top character of the stack, but we had to pop and push directly from the top of that stack. But now we can read anywhere on the tape where we currently are, and we can write where we currently are. We can also move along the tape in one direction or another. So that's what the states and transitions are going to describe. If we are currently looking at a particular character and we're in a particular state, then what do we write to the tape? What do we replace that character with? And then do we move left or right? So we don't have any restrictions on only moving left to right or anything else of the sort within our storage. We're still going to want to move left to right with respect to the input. But if the input is on the tape, now we can start moving left to right within the input as well. So if we throw the input, instead of it just being this arbitrary input that's passed into the program that we have to read, now if it starts on our storage, we can manipulate that in any way we want to. And that unlocks a massive class of languages that we can now represent. So no input file, no storage other than the tape. It's literally just the CPU, which is the states and transitions, the control unit, and it is this infinite tape. That's it. So the input that we would be reading otherwise is on the tape prior to the beginning of this algorithm. And the output will be what is left on the tape when the machine halts. Everything that happens between when it starts and when it stops is going to be the manipulation of the input into the output. So it really just looks like this. Pretty straightforward. Control unit, inside of that control unit are states and transitions. So think of it like a state machine is embedded in that control unit. And then the input and output are just on this infinite two-dimensional, infinite one-dimensional tape in either direction, but it's single dimensional. Because I haven't had too much success with this, I'm not going to leave the formal definition on there for too long because this just looks like a lot and it's not as complicated as this makes it seem. But the components of a Turing machine, we have internal states. This is the same as every state machine we've seen so far, like a Q1, Q2, Q3, Q0 embedded inside of that control unit. We have our input alphabet. We have a new character for the tape alphabet. This says this is anything that's legal to be on the tape at any particular point in time. So maybe we have some symbols that represent some middle point between the input and the output. There's also a new symbol for the tape alphabet called a blank. And this is going to be the equivalent of something like the null character or null in general. It represents that not just it's empty, but it's nothing is there. You don't want to, it's not the empty string, which is something that is there that's the empty string. It is nothing is there. So everything on the tape that is not the input, every other cell, infinite in both directions, starts blank. And that way you can say something like, I know I've reached the end of the input when I move right and I see a blank. That tells me I've reached the end. Then we just say we define an initial state. We define a set of final states, just like before. And now our transition function is a little bit more complicated. We have an initial state that we are in. We read a character from the tape alphabet, and that will define the state that we are in. That tuple defines the state that we're in, which state are we in, which input symbol are we looking at on the tape. The output from this is a new state that we go to, a new tape symbol that we are looking at, and whether we move left or right. So you're writing that symbol, basically that you're going to make a transition within the control unit from one state to another state. The character that's there, you're going to write another character. It could either be the character that was already there, or it could be yet another character that is different from that character based on some logic from the state that you're in, and then you move either left or right. Visually, it looks more like this. So we're in state Q1 internally in the control unit. We are looking at a cell that contains an A. What we want to do when we do this is we're going to replace the A with a D. I don't know why we're doing that, but we replace the A with a D as we move from figure A to figure B. We're moving internally in the control unit from Q0 to Q1 as we transition from this, and we moved right, such that now the read write head is pointed at the cell that contains the B. So that is the equivalent of one transition. That's everything that we need to consider and think of when we transition between one state and another. Is internal state changes, the character on the tape might change, and we're either moving left or right by a single cell. Any questions on the outline of what a Turing machine is or how it works?
Is this like a stack where we can also like do multiple move rights at once?
We'll actually talk about equivalences within Turing machines. So yes, that is equivalent and can be defined as a series of no op right, no op right, no op right, no op right to be able to do that, where you make no change to anything. You don't change the internal state. You don't change the character that's there. So just like we could have had a multi-edge in a DFA that consumes multiple characters, it's the equivalent of just having a bunch of different states, each of which consume one of those characters. It's very similar for this. So we'll define it as a single left or right to start, but we will talk about the kinds of Turing machines that you might be able to construct that would be equivalent, have the same computational power. Yeah.
So the middle D, so that's pretty much just stating like write this value inside the previous state.
Yes. So yeah, we're in state Q0 pointing at an A. When we are in that case, what we want to do is change the internal state to Q1. We want to replace the A with a D, and we want to move right one by one cell. So now the read write head is pointed here. Yeah.
We push blinks.
We can absolutely write blanks.
We kind of thought it looks like a W list.
Yeah, you could kind of think of it kind of like a doubly linked list that doesn't have a head or a tail. It's just infinite. You start somewhere. You start at the first character of the input, wherever that happens to be. And there are infinite blanks to the left of that, and the rest of the input is to the right of that, and past the end of the input, infinite blanks. Yep, null, 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 null on forever. Because you might need all of that space for a computation. This allows us to theoretically solve any problem where you might run out of memory. As long as it takes some finite amount of memory, there's no limit to the amount of memory that we can solve a problem with. If you have a computer with 32 gigs of RAM, 64 gigs of RAM, a server with 2 terabytes of RAM, it doesn't matter. There's still an upper limit to the size of the problems you can solve, because you can only, unless of course you're writing and reading from page files on disk, but there's still some upper limit to the amount of disk space that you have. There's an upper limit to the size of a problem that any given machine can solve. A Turing machine does not have that restriction because this tape is infinite. So it is a theoretical machine in that it's useful for solving arbitrarily large problems, but it also represents theoretically what could we solve if we had a machine with an infinite amount of RAM. Could we solve that problem? Yes or no? Which is interesting. Maybe there's a problem that we can't solve today. It would require just more storage than we have across all machines in the entire world. But maybe at some point, we create enough storage to where we can solve that problem. We can theoretically tackle that problem with a Turing machine in the meantime. So what is it? It's just a simple computer. It can do everything a computer can do, which is wild. You could put the source code for Elden Ring on a Turing machine. You could put the YouTube algorithm on a Turing machine.
That'd be a waste of space.
Just run 293.
But yeah, it's exactly what a computer is. If we define what that means, then we could have that as output. We would need some additional hardware to be able to produce anything visual, but we could at least play numerical Elden Ring without a GPU. So processing unit that has a finite amount of memory. What that finite amount of memory is defined by the problem we're trying to solve. The tape secondary storage is infinite. Instructions that the Turing machine can carry out is pretty limited, but when you combine these simple things into a more complicated structure, then you get the equivalent of any program that you or I could write. So it knows what symbols are on the tape. It can decide what to do next based on that. You can either rewrite the symbol at the current position on the tape, change the state of the control unit, and move the read-write head to a new position, either left or right from its current position. One thing to note, it's deterministic. This is not a non-deterministic machine. We can't fork this arbitrarily and create a ton of different threads. Although, it'll create an interesting question to say, can we simulate a non-deterministic Turing machine on a deterministic Turing machine? We'll answer that question a bit later. So we do know that the transition function, as long as we are in a particular state and see a particular symbol on the tape, there's only one possible next state from that. We can't branch from that and say, if we see an A on the read-write tape and we're in state Q1, we could either write a B and be in state Q2, or we could keep that A there and stay in state Q1. That would be non-deterministic. So there's only one transition defined for each configuration, which was that left-hand side of this expression, delta Q0A. We can only have one transition. This is not going to be a set of multiple possible transitions. For every one of these tuples, there is at most one of these. That's what's necessary in order for this machine to be deterministic. So, thoughts on the limitations of a Turing machine? I've already spoiled that it can do everything a modern computer can do, which is cool. What is that limitation? What can't a modern computer do? We had one example of that on the very last slide of the last slide deck, determining whether two context-free grammars accept exactly the same language. Why was that not possible? Yeah, we couldn't test every of an infinite number of strings. If the answer so far is we haven't found a difference, then we don't know whether the answer is that they accept the same language. We would have to continue to do that forever in order to be able to answer that question. So that means, what is the limitation of a Turing machine?
Can't test every string.
Yeah, it either can't answer yes all of the time, or it can't answer no all of the time. It would enter something like an infinite loop for at least one possible input. Then it's not an algorithm. The definition of an algorithm is it can answer yes or no to every possible input. It terminates or produces an output for every possible input. In order for a Turing machine to not be able to do something, or for a program that we write to not be able, an algorithm, then there would have to be some input where we enter an infinite loop and can't answer yes or no all the time, or always produce an associated output if it's a transducer. So what can a computer do that a Turing machine cannot? Nothing. There is no computation. They're equivalent in terms of the power of their computation, which is wild that something that simple can do something as complex as anything our computers can do. So let's start with how do we work this? How do we start to design a Turing machine program? We start with the control unit in its initial state. We'll call that Q0. We know that there is some input written on the tape. From here, we just go through the transitions. Each transition, because this is a deterministic machine, is going to be predetermined as to where it will go when it's in that state. So because of that, there is only one possible path from this initial configuration of the Turing machine to its termination. If we could see into the future, we could tell what the output was going to be for any particular input. It's the same as you write a program. I ask you, if I were to feed your program 4, what does it output? And maybe your program squares the number. You'd be able to tell me the program will output 16. So as we go through all of these transitions, the read-write head is going to be reading from and writing to the tape, turning the input into the output. The process can terminate. There is a final state that basically says if the Turing machine says we're going to halt, and we halt in a final state, then we accept. If the Turing machine halts, but halts in a non-final state, then we reject. However, what if the Turing machine never halts? What if we reach, there's a particular input type that never gets to a halting state. This is the equivalent of an infinite loop, where your program doesn't reach termination, where it says, all right, we're done. Here's the output. Something we've all experienced. So when the Turing machine, it's not just when it reaches a final state, when it reaches an internal state where it says there's like a Q halt. Or if there is a transition that is not defined. So we don't have, unlike a DFA, you don't have to state every possible transition. Kind of like an NFA, if a transition isn't defined, then it's an automatic instant reject. So that means that the transition function that we use is only a partial function. So it doesn't define for every possible input a guaranteed output for that. We know a function for every possible x value, there's an associated y value, and that's what's necessary in order for it to be a function. To be a partial function, there are some values of x that map to y, but there are some values of x that might not map to y, or might map to 2 values of y. That's not the case in this, but there might be some transition that's not defined. If it's not defined, we instantly reject. All right, let's see an actual example of a Turing machine program. Any questions before we dive into an example?
How do you really determine whether your program has accepted, if a halt state isn't necessarily accepted?
Yeah,
or
you go to
denied?
the halt, and depending on, did you halt when you were in a final state, or did you halt when you were in a non-final state? That'll determine
Which
the
is why it
difference.
contains sets of final, non-final states.
Yes.
Is there a way to design Turing machine to stop an infinite or to catch an infinite and stop it and it gets into?
That is a phenomenal question, and we're actually going to answer that question by going into, this is a large question in computer science. It's called the halting problem. And we're actually going to go into the halting problem, because you've heard of that before? Yeah, that's exactly the question that the halting problem poses, is can we detect an infinite loop? Can we? Yeah, the answer is no, we can't, but why is pretty fascinating, and we're going to dive into exactly why it can't do that. And I show one video in this class because it's really, I don't have the level to be able to do the visuals that Veritasium can. I don't know if people know Veritasium on YouTube, but yeah, one of his videos goes over the kind of the flaws in mathematics, and one of those flaws involves the halting problem and Turing's thesis as a way of talking about, is math, what's the word? Is it deterministic? And in this case, there are inputs, there are problems where we can't solve a particular problem, because in order to solve that problem, we would have to be able to solve the halting problem. So kind of like this NP completeness web, that if we solved one problem, we'd be able to solve all of them and show that they're all deterministically polynomial. then we would be able to say something similar with the halting problem. If we could solve any of these problems, we could solve the halting problem. Since we can't solve the halting problem, we can't solve any of these problems. We'll get into that in a bit. Fascinating topic.
Oh, stuck in a tautological loop. That's not good.
It actually, we can show, we have proof that the halting problem is not solvable. It's not an open question. It is proven to be impossible. Which means that there are other questions in math that we can't answer, because if we could answer them, we could solve the halting problem. So let's give you an example of a Turing machine program. So here is a Turing machine definition. This tells us the states in the Turing machine are Q0 and Q1. The input alphabet is A and B. The symbols that can be written on the tape are A and B and blank. Q1 is a final state, and then it defines 3 transitions. If we read an A and we're in state Q0, then we will stay in state Q0, replace that A with a B, and move right. If we're in state Q0, we see a B, we stay in state Q0, we replace that B with a B. That's the equivalent of a no-op. You're not writing anything different to the tape. And you're moving right. If we're in state Q0 and we see a blank, then we go to state Q1, which is our final state, and we write the blank, replacing the blank, and move left back to the last character, and that's what halts the machine, is that we reach this state Q1 that is the halting state. So if we're able to reach Q1, then we halt and accept. Otherwise, we reject. So let's look at a potential tape. This tape has AA on it at the beginning. What happens? We start in state Q0 with the read write head looking at the first A. See if you can take a minute or two, follow these transitions, and see if you can figure out what is on the tape after this program halts or doesn't halt. So I guess question 1, does this Turing machine halt? 2, if it does halt, what is left on the tape? What is the output of this Turing machine?
Tape right now, would that first A turn into a B then?
Yep.
My other question is, would it move from that B we just wrote to the next A though?
Yes.
Okay.
Yeah. So that happened. The writing happens before the move.
Okay. So it will move.
Yes.
So that after we read that second A, it moves over to that blank state and then we read blank.
Yeah.
Okay.
And then it would move back left, point at the now B that is at the end, and halt. So here is kind of a visual of step by step, the 4 transitions that this would go through. We start state Q0 pointing at this first A. So we read this transition because we're in Q0 on an A. This says that we're going to stay in state Q0, so the following state is also Q0. We're going to replace the A with a B, which is what we see at time step 2 here, and then we move right. We're pointing at cell number 1, even though it's infinite in that other direction. We're going to call that cell number 1 for the moment, and we move over to cell number 2. Then we're in state Q0 pointing at an A. This is familiar, it's what we were just doing. So we're going to follow that same transition again, staying in state Q0, replacing the A with a B, and moving right. Now the state that we are in is Q0 looking at a blank. Q0 looking at a blank is defined that we are going to move the state Q1. We're going to write a blank, so this is still a blank, and we move back left. Now that we're in state Q1, this is determined to be the halting state, so we are going to stop and accept, because Q1 is an accepting halting state. Questions on that? All right. Let's look at what is it like to try to draw this as a transition graph. So we can express Turing machines with transition graphs, just like we could with DFAs, NFAs, NPDAs. However, if we wanted to do something like to represent the machine from the last slide, it would look something like this. So each transition is defined with a triple. What we read, what we write, where we move. So this says there's a loop from Q0 to Q0, reading an A, writing a B, moving right. There's another one, reading a B, writing a B, moving right. And we can transition to a final state Q1, reading a blank, writing a blank, and moving left. What we have now is a transducer. This did accept, but what is on the output tape is the output. Fascinating. This just converted any string of A's and B's to all B's. So we're not just accepting and rejecting. This accepting now says the program terminated, which is very similar to how you might expect a program that you wrote to behave. Great, it terminated, but did it terminate and actually give me the output I was looking for? I'm sure we've all written a program where we forgot to print the answer, and so the program terminates, said, I did everything you asked me to do. And it's useless to you because it terminated and then lost the information that it was calculating along the way. So accepting and rejecting is just the program terminating or not terminating. And the transducing part of that is what's left on the tape. What is your output when you do that? So I'm going to give you a transition graph, and your task is to tell me what this does. So assuming the tape has an A and B in that order, the read-write head pointed to the first character, that A. What does the machine do? Here it is. It doesn't do jack.
It never stops because there's no final state.
Well, there is no final state, true. But yeah, no matter what you do, you're going to be ping-ponging back and forth between Q0 and Q1. There is no legal setup that allows this to terminate. So imagine that there's A and B. So you read an A, write an A, move right. Now you're at the B. You read a B, you write a B, you move left. You read an A, you write an A, you move right. You read a B, you write a B, you move left. So this just does this forever. So this is one way that you can just represent something like the logic of an infinite loop with a Turing machine, which is really interesting to think about. Questions on why this is an infinite loop?
It doesn't change anything.
Yeah.
Or like clarification, so like it's an infinite loop because like it keeps reading and writing itself basically, right?
Yeah, it's writing the same thing, so it never changes what's on the tape, and then it's ping-ponging back and forth between these two states and looking at, since the input is just an A and a B on the tape, it's gonna go back and forth between looking at the A, looking at the B, looking at the A, looking at the B, being in state Q1, being in state Q0, Q0, Q1, Q0, Q1, A, B, A, B. Yeah, there's no defined end to this. So you can absolutely, just like you can write a program that has an accidental infinite loop in it, you can write a Turing machine that has an accidental infinite loop in it. You can write a program that has a purposeful infinite loop in it. You can write a Turing machine that has a purposeful infinite loop in it. So we can model these configurations within a single image. Just like instantaneous descriptions of NPDAs, we want access to the current state of the control unit, the contents of the tape, and the position of the read-write head. So it looks something like this. We're going to define state Q that we're in. We're going to define everything before the read-write head as x sub 1, everything including where the read-write head is pointed and after as x sub 2. And now we can state with a single little, this is impossible to read. This says A1, A2 up to A sub k minus 1. So you're going to write as a string the contents of the tape from the first character that's on the tape up to this point. Then you're going to specify the state that you are in. Then you're going to include the rest of the tape. And that tells you everything you need to know about the description of where the Turing machine is within one string. So contents of the tape, where is the read-write head pointed? It's pointed, you see, you state the name of the state right before the A sub kth character that is on the tape.
X2 doesn't include the head. The head is just in the middle, but your little graphic shows that it's in X2. Is that correct?
Yes, because it happens after the state. So here's, this is still impossible to see. A sub k minus 1.
Yeah.
The next thing that happens is the state Q. The next thing you see is the state A sub k. So this happened, this is written after the state, which is why it's in X sub 2. Yeah,
I remember, like a previous slide, there's like a bigger box above the tape, which is a control unit. So-
yeah, this is just the part of it that isn't the control unit. So all the part of it that is the instantaneous description is just this string right here. And we're mapping this string to this visual representation of the Turing machine. So there's also a control unit in here. It just doesn't matter what the actual states are within the control unit. All that matters is the current state that it is in, which we're just saying is Q here. Great question. Anything else? So anything else is assumed to be blanks. So anything past the end of A sub n, blank. Anything before A sub 1, blank. Just like before, we're going to use the turnstile symbol. So what we call this symbol, turnstile symbol, looks kind of like a turnstile. So let's go ahead and say, if a transition from Q1 on a C leads to state Q2, we replace the C with an E and we move right. The tape contains A, B, C, D, the read-write head is on the C. We can show that this transition happens using this turnstile symbol of saying, moving from one instantaneous description to the next. So how would we do that? Using the concept of that instantaneous description. What is the initial state? So we said the tape contains A, B, C, D. The read-write head is pointing to the C. And we're in state Q1. So what is the instantaneous description for the Turing machine in that state? We have A, B, Q1, C, D. Yep. So now we can use the turnstile symbol and say that we can get to this following instantaneous description. What does the instantaneous description look like after we have made this transition? ABQ1CD to an ABEQ2D. The way we get there is we know that we're replacing the C with an E. So this C gets replaced with an E. We moved from state Q1 to Q2, so the state that we write is Q2. And we moved right, so the position of the Q is going to be one position to the right of where it was in the string. It just moved past the C that has become an E. So this is just one way to show, here is how the tape changes and the state changes embedded inside of one. So this is an instance of running through your Turing machine. You can see a run through of that by just a sequence of instantaneous descriptions. Next question we might want to ask. We already figured this out, and we've already talked about it a little bit. Is it possible to produce a set of instructions putting a Turing machine into an infinite loop? The answer is yes, and we will come back and study the halting problem because it's so cool. Where we're transitioning from here is we're going to start looking at how can we use them like we have used the other state machines that we've seen so far in the class. So just thinking of them for the moment as language acceptors, even though they can do really cool things, we're going to limit them to doing what we have done so far with regular languages and context-free languages for the moment. So we're going to assume that the input is written on the tape, blanks are on every space not used by the string. That's the main assumption that we make. We know that the Turing machine starts in its initial state. The read-write head is pointed at the leftmost character in that input. Then we can accept the string if the Turing machine is in a final state and has halted. We don't allow blanks in any portion of the string because otherwise, how do you determine where the end of the string is and or where there are blanks in the middle of the string? There's no way to know that. Even if you go right on a blank, right on a blank, right on a blank, right on a blank, were there that many blanks between the first part and the second part of the input? Or are we past the end of the input? That's an ambiguous problem. We have to remove that ambiguity in order to be able to answer yes or no to something. So we do not allow blanks in the middle of our input. Yeah, so if we did allow them, we would have ambiguity. So if we want to reject, two ways to indicate failure, you either halt in a non-final state, or you enter an infinite loop and don't halt. Unfortunately, entering an infinite loop cannot be recognized because of the halting problem. So that becomes kind of a problem. But we will see how we can utilize this concept of entering an infinite loop to make claims about other languages in a very interesting way. So we will actually utilize this and then go into an infinite loop as something that actually has meaning and relevance. Yeah.
This is kind of not totally connected, but does a Turing machine have like memory in the sense the previous one, the automaton?
Yeah.
Does it have any kind of memory like that?
It is on the tape.
That's the
So
only-
yeah, we're going to utilize the tape. It can be something like if we read this and we want to document something about it, move past the end of the string and write something. So we can utilize the entire tape as the working memory for the program,
So you
aside from the input.
You can use like a tape position as like a register.
Yes.
Wow.
Yep. Yep, you can use it as a register, you can use it to represent RAM, you can use it for, it's kind of like any of that. It's just a matter of how fast is it. And what's nice about a Turing machine is it's all theoretical, so we don't care about how fast it is.
Theoretically now.
You wanted to like partition your tape, you have to have like many like no ops in order to get to the new like block.
We're actually going to talk about that as well, because there are many different variations of Turing machines that the question we're going to want to ask is, can they represent, can they accept the same class of languages? In that case, what can we do to a Turing machine? Why is there only one tape? Can we have 10 tapes? Can we have an infinite number of tapes? Can we have Can each of these tapes be two-dimensional instead of one-dimensional? Can they be three-dimensional instead of? Interesting questions. Does that change the power of the Turing machine? Does it allow you to answer questions that you couldn't answer before with a single tape Turing machine?
Might make some processes easier, but if we already have infinite, storage and it's access at all times, is it really?
Yeah, that is exactly the question we're gonna be asking over the next couple of days. So we'll come back tomorrow and start answering those questions. We're just glad to be past the pumping lemmas, aren't we?
Until we have to come back to them.
Yeah. There, we're done after the context of pumping lemma. Once you have the homework on that, maybe an exam question, maybe not, we'll see. Then no more class time dedicated to it unless we're ready.
If you want an index, your take, it has to be all relative, right?
Yeah.
So is there a way to like? You can only have one symbol per cell, so there's no way to like really tell. Just by reading one cell where I want my header to go after, right? I have to like make a sizable partition.
Right. Your question, I'm gonna try to answer it. Let's see.
This doesn't.
I love this stuff to Kyle Hill, I don't even know about.
The answer is both. You can't determine before running the program and you can't determine while running a program. Because you can't determine if you're in exactly the same
Kyle
time.
Hill's video about how
You can't determine if you made some kind of progress toward that when you're terminating.
It's a magic deck where you draw them from.
If you do exactly what.
Pretty much have this set up where you're can't do anything, then you have your infinite
But
tape
the question
on
about
this, but it's by
a little bit.
reading your
That I run a general program.
color,
We will
power,
say,
and
I take as input a program, I want
whether
to
it's
to if to show mine.
you play.
Question.
I think I have to write this.
Yeah. So we first need to come up with an idea of an example string with W. You don't want to instantiate it as W. You want to use a language class that we've seen before that might help. So you can use something like W equals A to the N B to the N. Then W equals A to the N B to the N, A to the N B. Then you can attach yourself to the proof of A to the N B to the N not being context free to say, well, WW contains one such W like.
Wait. We're gonna have A and an L, and A, so we need to determinate.
Yeah, you could do that.
This we can keep, we just need to make this a C.
Is that the only constraint to that problem? Yeah, there are more A's than there are B's. This is no one, this is L. There are more A's than B's. The issue is that M is not greater than or equal to M plus one. So you have to choose an initial string that's in the language.
Not great with the L.
So you could do A to the M plus one, B to the M. But since it allows it to be
Minimal
equal,
one.
we can do A to the M, B to the M.
Times.
I just don't get where you have C.
But if it was.
So you have to do this if E, or the D running on B.
Well, I guess it would just be that same word as the last time.
You can use I equals 0 to pump down.
Okay.
And if they're basic to each other, down, now you know there are fewer A's than B's.
Represents the combination of B, A, B, B.
I'm gonna try to clean this up. Back and forth with A.